So this is a close-up of a coral polyp, and these red dots are the individual algae cells, so the symbionts that live inside the coral tissue.
Coral reefs are gigantic, but corals themselves are very small. And the things scientists like Ruth Gates at the University of Hawaii need to know about corals happen at such small scales that it takes $1 million microscope to see them.
This is a laser scanning confocal microscope. It's the only microscope in the world that allows us to image corals live in simulated future ocean conditions that are warmer and more acidic, and we can watch the response on the microscope of a living animal. It's remarkable technology.
Why do they need to look close enough to see inside a coral? Because corals are in trouble, and the solution to their rescue might be within. Corals around the world have been declining for some time, but the years from 2014 to 2017 were devastating. Abnormally high water temperatures caused a global bleaching event, only the third ever, and the longest in recorded history.
For the past few decades, we've lost about half of the world's coral reefs. In the last 3 years, we lost another 20% of what was remaining. The problem is, as the oceans continue to warm, we're going to lose more and more corals. In fact, climate models are predicting that 90% of the world's coral reefs will be seeing the temperatures that cause bleaching every single year by mid-century.
The reason hot water causes corals to die off is well understood. Corals have algae called zooxanthellae living inside their cells and giving them energy through photosynthesis. The algae can also get too hot, and when they do, they release chemicals toxic to the coral. The coral ejects the algae and turns white or bleaches. But Ruth and others have found that some supercorals bleach less easily or recover faster. Now they can start to see why.
By using the confocal microscope, scientists can go in, find these corals that are more tolerant to high temperatures, and potentially use these for breeding to try and develop supercorals.
These bright green patterns that you see, those molecules protect the algae. We actually don't know why they're important in the system, but that's why science is so amazing. We're always looking at discovering new phenomena.
They do know that corals can host different types of zooxanthellae, and some of these might be super algae that do better in high temperatures and acidity too. And if that's the case, can scientists help to make that relationship even better?
One strategy that we're looking at is to try to give corals the best zooxanthellae they can possibly have. And so can we take the ones that aren't very good at facing temperature out of the system and put back zooxanthellae that are better at facing higher temperatures and surviving?
Corals take hundreds to thousands of years to adapt to warming conditions, and we don't have that long. By breeding supercorals through this process known as human-assisted evolution, and finding the best algae to go with those corals, we may have an opportunity to try and do in just a decade or two what the corals would do over hundreds or thousands of years. Over the last 10 years or so, there's been a great advance in using coral nurseries, fragmenting corals and growing them back and putting them out on reefs. But you can't restore a habitat when the problem is still there. And as temperatures rise, we need the supercorals. We need those corals that can tolerate high temperatures. So the challenge for the next scientists, the next engineers, is to find those answers of how do we grow them faster, how do we grow more of them, how do we plant them fast enough to be able to spread corals out and restore coral reefs all around the world. That's what we need to make a coral comeback.